Everyone, firstly, I would thank the organizer for this chance of my presentation. So my topic is kinematically complete experiment for ionization and excitation of helium near the threshold. So we start with this very old but very famous paper. In this paper, the authors investigated 2 or 3 electrons escaping from a nuclei in the threshold, near the threshold. They predicted some general behaviors for such process. Here I list out some general behaviors for single and double ionization of helium. Firstly, the cross-section will fit the power law form as a function of the excess energy. Secondly, for 2 electron emitting electron induced single ionization of helium, the 2 electrons will be emitted back to back. This is because in the threshold region, the excess energy the 2 electrons could share is very, very low. It's even much lower than the binding energy. This results to the same repulsion for these 2 electrons from each other and a similar attraction from the nuclei. Thus, the net force for these 2 electrons are almost the same. And then it forms a very symmetric emission pattern. For 3 electron escaping process, electron-induced double ionization of helium, then it will form also a very symmetric configuration, the 120-degree configuration. These have been experimentally confirmed by the in a kinematically complete experiment performed in Icpeac. So what we focus on is this process, the ionization and excitation with simultaneous excitation of helium. In such a process, all 3 electrons are strongly involved in the interaction, but finally only 2 of them could escape from the nuclei, while 1 of them will be captured by the nuclei. So this is such a system could be a very ideal system to investigate how the 3rd electron, the bond to the nuclear electron, influence the threshold behavior of the 2 outgoing electrons. For the measurement, most of the experiment for ionization and excitation process, they use the E2E method. That means they measure the 2 electrons in the final state and then could get the binding energy spectrum and determine the principal quantum number from this spectrum. But the 2s and 2p state could not separated since the binding energy for these 2 states are almost the same. A proper way to identify the 2p state is detecting the photon emission here. Since we know the 2p state is will decay very fastly, but the 2s bit is metastable state. The lifetime is much longer. So the photon here could be a fingerprint for this 2p state. In our experiment, we detect 1 electron, the helium ion, and the emitted photon in triple coincidence. And we could reconstruct the momentum of the other electron due to according to the momentum balance. So this is our setup. A pulsed electron beam collide with the helium jet produced by the supersonic expanding. And then we use the uniform electric field and magnetic field to guide the ion and the electron to the detectors. We equipped 2 photon detectors to this reaction microscope. These detectors could detect the photons with an emitting angle less than 15 degrees with respect to the axis perpendicular to both the beam and the electron beam and the helium beam. The incident energy in our study is chosen as 17.4 eV. The advantage of such an arrangement is that it's lower than n equals 3 state, so only ionization excitation to n equal 2 state could be opened. And in addition, we detect this photon and we could select the 2p state. Such arrangement also take challenges to the experiment. First, the challenges are from latest efficiency and acceptance for photon detection and further reduced efficiency for multi-coincidence measurement. And the last but the biggest challenge is the low cross-section at the threshold region compared to the large noises. Besides the ionization and excitation process, there are also other process opened. Firstly, the neutral excitation, and following this, the excited neutral helium atom could decay and emitting a photon. And in addition, the single ionization process could produce a lot helium ions and electrons. The cross-section for both the two processes are 2 or 3 orders higher than ionization and excitation process. So random coincidence could be formed from the photon here and the ion here and this electron. They could easily submerge the real ionization and excitation events. What we do is, here we say the random cross-section, the random coincidence cross-section is proportional to the cross-section of these two processes. So it is proportional to the square of the electron, the current of the electron. However, the ionization excitation process is only proportional to the beam current. So if we reduce the beam current, the random coincidence events will decrease more fastly than real events. The first step, we reduce the beam current to a reasonable level. At the same time, it means a decreased efficiency for detecting and a long time for the measurement. After this, we get a map which could guide us to find the true ionization and excitation events. This axis is the time difference between the helium ion and the detected electron. And this axis is the time difference between the electron and the photon. From this map, we could identify that the ionization excitation events are here. And the structures here and here are from random coincidence. So the next step is we select these events and analyze them. we reconstruct the momentum of each electron and get the energy sum for this for the two electrons. We are very happy with this plot. Here we find a peak with the binding energy to n equal 2 state, and the baseline here are very low. That means noises are well eliminated in our measurement, and we achieved a success measurement for ionization excitation in the near threshold region. Then we plot the cross-section as a function of the cosine theta. Theta here is the angle between the two emitted electrons. In this plot, it contains all the recorded ionization and excitation events, regardless of the energy sharing and the emitting angle of each outgoing electron. That means they are high integrated. We found two feathers, 180-degree peak. Here is a zoomed view of this peak, and another 120-degree peak. To trace back what's the reason for these two peaks, a calculation based on the firstborn approximation is performed. After this, the calculation is modified by this factor called Watt-Mark factor. Because the post-collision between the two electrons could not be ignored here. This calculation is performed by Professor Whelan from ODU and Professor Waters from QU. Here is the result. Since the magnetic quantum number for 2p state could be 0 or could be minus plus 1, the calculation is performed in these two different cases. And in addition, the calculation is only performed with a particular case kinematic condition. I want to emphasize that here we do not want to exactly reproduce the measured cross-section, but to find out the reason for the observed structures. Then here we fix the emission angle of one electron and the magnetic quantum number, and plot the emitting angle of the other electron. We found that for M equals 0, we get a back-to-back emission, but for M equal to minus plus 1, we get we get an angle between the two electrons around 120 degrees. So this calculation may suggest that the observed structures in our experiment may arise from the different magnetic sublevels of 2p state. So this is a very latest result, and the theoretical works are still working on. They will calculate TDCS for different kinematic conditions to check what will be the result. Then the summary and outlook. We performed a success kinematic complete measurement for ionization excitation to 2p near the ionization threshold. In our measurement, both the principal quantum number and the angle momentum quantum number are determined. We observed two peaks. One is for back-to-back emission, and the other one for 120-degree emission. Compare with the calculation, the calculation suggests us that the two feathers observed may attribute to the magnetic sublevels of the helium-2p state. And more important, the good performance of our setup in this very low cross-section region may indicate that we could get 2p or 2s and 2p some fully differential cross-sections in the future. Such data would offer the most stringent for theoretical models. At last, I would thank my colleagues, Professor Ma and other colleagues in Lanzhou, and Dr. Xueguang Ren and Dr. Alexander Dong in Heidelberg, and Professor William, Professor Walters for their calculations. Thanks for your attention.